Okay, can you guys hear me out there? Can you see the shared screen as well? It says selectivity of radical CH substitution for halogen. So I'm doing this a little bit different this time because I have a little bit of issues with the document camera getting everything sort of on the screen at once. So what I'm doing now is using my iPad, and I have an app that I can draw on as a whiteboard. So we'll see how this goes. If there's negative feedback, I'll switch back to the doc cam. Just let me know what you think. But what we're going to do today is continue on with the worksheet and how what we initially talked about in terms of the substitution of primary versus secondary for propane, how that is relevant to the worksheet, and how the chapter 10 material is relevant to what you're reading in chapter 6 with thermochemistry and kinetics. So again, normally in other textbooks, all this stuff is sort of put into context. So let me just briefly go over. Hopefully you can see this little laser moving on the screen. This is propane, and as we've known over the course of this semester, how to classify primary versus secondary versus tertiary hydrogens. So propane has two equivalent sets of hydrogens. You have the primaries, which are methyl groups, then the secondaries, which are methylene. So all I did here was just count them. So there's 3, 6 primary, there's 2 secondary, there's no tertiary, that gets us a total of 8. So 6 over 8 is 75, 2 over 8 is 25. So that's just simple observations in classifying what is there. So the reason this is important and the reason you learned about spectroscopy so early is that when a reaction is run, you can get more than one product, and you have to know how you can, in reality, differentiate those things. So here we have a product distribution where we've substituted a primary, and then here we've substituted a secondary. These are the expected ratios, 3 to 1, or 75-25%, however you like to think about things. So what we saw before, notice here I've drawn XX. So we've saw where X2, this is molecular halogen. We've saw where X2 is chlorine. The actually observed ratio, the observed product ratio is 45% of primary versus 55% of secondary. Now, if we take both of these and divide by 45, we get 1 to 1.2. This new term here, relative reactivity, we're taking that isolated yield, we're dividing it by the number of hydrogens that are primary, which is 6, to get 7.5. For the secondary, we took 55%. There were 2 secondary hydrogens, we got 27.5. Now the ratio of that to that, which is shown here, secondary to primary, is 27.5 divided by 7.5. That is telling you the secondary hydrogens in the starting material, which I'm highlighting, are 3.7 times more reactive than the primary. So this is what we aim to understand in chapters 6 and 10. Even though from statistics you're expecting a 75 to 25 ratio of these two products, in reality, the secondary hydrogens, which there are less of, are more reactive. So the definition of relative reactivity, again, is the observed ratio divided by the number of those type of hydrogen. 45 divided by 6 is 7.5. 55 divided by 2 is 27.5. What you're doing here is comparing the types that are present in the molecule. So secondary over primary, you're just taking those numbers as the quotient. And it's telling you the secondary hydrogens are 2.5 or 3.7 times more reactive than the primary. This is the analysis when the halogen is chlorine. What if the halogen is bromine? Now we're using BR-BR. The H nu, that's light. The delta is heat. So for a radical substitution, you're using a molecular halogen and light or heat to initiate the reaction. So these are the conditions. So let's look at the data for bromine now. So the observed ratio, when we have bromine, you get 3% of the primary substitution product and 97% of the secondary substitution product. So what is that ratio? Again, we're taking both of those numbers and dividing by 3. So we get 1.0 and 32.3. So let me ask you a question and you can answer in the chat. Using this analysis here of relative reactivity, what number should I write here and here for bromine? So for bromine, the relative reactivity of the primary hydrogen should be what? So Aiden says 3% divided by 6, that gets us 0.5. And then what about the secondary? So 97% divided by 2, that equals 48.5 as we see in the chat. So now using that same analysis as we did up here, what number should I write here for secondary versus primary? So Aiden says 97 times more reactive. So we're taking 48.5 divided by 0.5. That gets us 97 times more reactive. So what you really need to understand, I think this is a crucial moment in your learning of organic chemistry, because number one, you are learning about an actual reaction, so CH substitution of H for halogen. You see the conditions necessary to achieve that. You see the product distribution. The main thing you want to take away from this, whether you start with propane, it don't matter whether it's with chlorine or bromine. Propane is propane. What this data is telling you is that depending on the halogen you use, the primary versus secondary product distribution changes drastically. So what we're going to do in this worksheet is we are going to understand why that is. The energy to cleave a primary CH versus secondary CH is the same no matter what halogen you're using. But the cleavage of this bond in the formation of these different products will require different energy. And so that's how we explain why you get different product distributions. So are we clear on this logic of chlorine versus bromine? So the words I'm going to start using for chapter 10 specifically are sort of associated. We can see this is relatively the same for the most part. So we're going to use the words reactivity versus selectivity. You can see that with bromine, we're getting more of this product where the substitution has occurred at the secondary position. Now I want you to think about the practical aspects of this. Again, not all of you are going to go into chemical research, but if you're running a reaction and you're trying to produce one thing, the bromine is the reaction you want to use because you're getting more of one thing. You do not want to run a reaction where you're getting a one-to-one mixture of something, because that means you have to put time and effort into separating those two things. So let's go ahead and move on to the worksheet. Again, we're going to use the data that's presented in this table. This is table 6.1 from the Klein 3rd edition of your textbook. And again, I'm going to primarily use kilojoules per mole in the calculations that we do. It's the more accepted unit. So again, when you're looking at any sort of table, you want to understand what this means. Bonds to H, CC bonds to methyl. So here we have secondary, or excuse me, this is primary, this is secondary, this is tertiary, and this is XX bonds. So we're going to go on sort of a treasure hunt where we're looking for specific substrates and what these values are. So let me just briefly show you on this slide what these bond dissociation energies mean. So for example, I'll try to squeeze it in here. If we're looking at this HH bond, what exactly is this number telling us? It's a reaction where the bond is homolytically cleaved and we're generating two hydrogen radicals. So wherever you see the red bond in these substrates, remember this is a homolytic cleavage, meaning that each species of that bond is getting a single electron from the bond. This is table 6.1. It's posted in Canvas and it's also in your textbook. So we started filling this out yesterday. I'm just going to quickly plug the numbers in. And again, if you have, you probably want to print this out if you haven't, just so that you can refer to it, or if you have the hard copy of the book, you can find the values pretty easy. So I'm going to just go ahead and plug these numbers in because we did it on Monday. And again, we are looking, keep in mind what we're doing. We are looking for the specific CH bond in each of these types of molecules. So methane is 435. Again, I'm not going to write the unit because it's going to get pretty repetitive, but keep in mind we're using kilojoules per mole. Ethane is 410. Primary in propane, we're going to use the same value, 410. Secondary in propane, 397. The tertiary in 2-methylpropane, that's 381. So you should make sure that you're finding the same value so you know how to interpret the table. Okay, so the primary in propene is 364. The primary in methylbenzene is 356. So those are just looking up those specific things in this table again. Again, make sure you're familiar with that in the intent of the question. Next, any questions on that? Okay, so the next slide, we're on question 2 where it says, draw the structures of the radicals of each molecule from part 1. Draw resonance contributors for structures that have hybrids. So again, I'll draw the reaction for methane, but for everyone after that, I'm just going to simply draw the radical structure. So there's methane. We're homolytically cleaving the bond indicated. So hydrogen gets an electron, and then carbon gets an electron. Again, it's important to understand this is called a fish hook. So that sort of looks like a fish hook. It doesn't have the full arrowhead. The fish hook means you're moving one electron only, and it's going to the indicated atom of the bond. So what are we forming here? We are forming methyl radical plus hydrogen radical. So the remainder of what I'm doing, I'm just simply drawing the radicals from problem 1. So for ethane, so I want to put the radical above the carbon because that's where it's residing. Propane, primary. So the other thing I want you to be cognizant of, cognizant means aware. So look how many things are bonded to this carbon, to this carbon, to this carbon. Should there be a formal charge on a carbon radical, yes or no? So I see a lot of yeses in the chat. So notice I have not drawn a formal charge so far on any of these. So let's go ahead and review the formal charge calculation. A radical is a reactive intermediate that is neutral. It does not have a charge. So let's say formal charge of carbon, formal charge of carbon radical. Carbon is in group 4. We're subtracting the 1/2 of the bonded electrons. So how many total bonded electrons are on this carbon? Total bonded on the methyl radical. So I'm looking for the total number of electrons in all the bonds. Remember, a bond is 2 electrons, right? So 6 electrons. So 1/2 of 6. Now the last term is minus the lone pair unpaired electrons. There's 1. So when you run through that, you have 4 minus 3 minus 1. That gets you 0. So radicals are neutral species. They do not have a formal charge. Even though they do not have a charge, they are reactive. They're more reactive than the just plain sort of methane carbon that you see in the starting material here. So there's primary. Let's do the secondary for propane. So the last one, we have 2-methylpropane. So maybe I'm going to draw that in the bond line formula now. So that's the radical that results from abstraction of the methine CH in 2-methylpropane. So let's classify these. So we have, up here we had methyl. We have primary, secondary, tertiary. Now we had propene. We said that was primary. So there's propene. We're abstracting a primary hydrogen, so the radical ends up there. For this, we can have resonance. So the double-headed arrow that I just drawn, that's the resonance arrow. That means the radical can be delocalized. Then the last one was 1-methylbenzene, where we wanted the primary. So methylbenzene is also called toluene. If we abstract a primary hydrogen, we get the following. Now we can delocalize that through resonance as well. Now I know 2 semesters of organic chemistry is a very long time in your life, but it's not that long. If you understand resonance in the movement of a radical, a plus charge, or a negative charge, organic chemistry 2 should be very straightforward for you. So let me show you how the radical moves in resonance. I'm going to throw some numbers in here. I'm going to say 1, 2, 3. 1, 2, 3, so I keep the numbering the same. So we're moving 1 electron here, then the pi bond is cleaving, so we're reforming the pi bond between 1 and 2. And then the other electron in the pi bond goes on to carbon 3. So this radical comes down. We cleave the pi bond between carbons 2 and 3 to form the new pi bond between 1 and 2. Then the single electron ends up at 3. So that's resonance delocalization. Again, it's important that you understand conceptually what resonance means. If somehow someone invented a means to see this molecule on the atomic scale, you would not see 2 discrete structures. These things exist in the same place at the same time. What this is telling you is that carbons 1 and 3 have radical character, and the bonds between carbons 2 and 3 and 1 and 2 have double bond character. So it's something to wrap your mind around, but that's conceptually how we think about it as scientists. Now look at the bottom case here for the methylbenzene or toluene. Notice how the resonance is the same in terms of the pattern. If I number 1, 2, 3, 1, 2, 3. So the point I'm trying to make here is that for resonance, you always have to have 3 atoms involved. One of them is going to be a radical, a single electron, an anion, 2 electrons, or completely electron deficient with a carbocation, or a positive charge. The other 2 elements or atoms in that 3-atom system must have a pi bond. So notice how this is repeated throughout. Now in this second structure, there's your radical. You have 1, 2, 3. There's your pi bond. The third structure, there's your radical. 1, 2, 3. There's the pi bond. The fourth structure, radical. 1, 2, 3. There's your pi bond. These are benzene rings, so they're 6-membered rings. They're hexagons. So another thing I want to point out here, again, this is a primary and this is a primary. Even though they have resonance, they're classified as primaries. So this is where there's where you cannot make assumptions when you do these classifications. There's always a twist to learning this. So what we're going to do in the next problem is rank the molecules in ease of hydrogen atom abstraction. So we saw from the table that the methylbenzene had the lowest energy at 356, so that's the easiest. And I'm going to put in the indicated hydrogen that's being abstracted. Now it's important for you to understand what these numbers mean. The ease to abstract that specific type of hydrogen. Again, I've been asking you throughout this semester, when you classify or how many unique sets of hydrogens does a molecule have? How do you classify them? This is where we're synthesizing all of that stuff into solving now problems related to reactions. This was plus 364. The 2-methylpropane was plus 381. The secondary for propane was plus 397. The primary for propane was plus 410. Ethane, we'll use the same value, plus 410. And then we finally have the methyl. That's plus 435. So does everyone understand the correlation that I'm making here by saying easiest to hardest in relation to the ease of abstraction? If you think of yourself as you're starting at 0 energy and you're applying energy into the system, you're hitting the lower number first. You hit 356 before you hit 364. So if you have a molecule that has both of these types of hydrogen atoms, this one gets abstracted first. So what I meant before by don't fall into the trap here, we have primary, tertiary, secondary, primaries, and methyl. So in general, the radical stability order will follow that order, but what you have to consider is when it's primary, such as in these cases, if it can have resonance, it sort of leapfrogs in front of the tertiary. So this is where the eye for detail comes in. Questions on this so far? So trust me, we are building up to some logic here. It gets a little bit more complicated, but I think this worksheet really condenses Chapter 10 in parts of Chapter 6 to put everything into context. So Blakely, I think, yeah, they may be sort of synonyms in a sense, but the word abstraction is more appropriate. The hydrogen is being abstracted by another species, and so that's what we're going to get into on the next page, or excuse me, 2 pages from now. First, I want to cover some more types of hydrogen atoms you will encounter. So this says find the enthalpy change values for CH hemolysis of the indicated bonds. So now the main difference here is, in this case, what is the hybridization of this carbon? So where the laser's pointing, that carbon, this carbon, and then that carbon. So those hybridizations are sp2, sp2, sp. If you're paying attention, the prior cases on the previous page, those were all sp3. So now the energy to cleave this indicated bond here is 464. To cleave this bond, 473. And then finally, for this bond, it's a whopping 547. So those are much, much higher than hydrogen atoms bonded to sp3 hybridized carbon. So we've made a distinction. So all of these, for this example here, all of these only have one unique type of hydrogen. So the next question says, why are these values significantly greater than those of part 1? So Ian says the third example isn't on the chart. That is correct. I got the number from a prior table from a different textbook, and I'll post that in Canvas. So as I said, to answer this question here, why are these values significantly higher? The radical so a radical is a single electron. Either ends up in an sp2 or sp hybrid orbital. And so how do we further understand that? How is the CH bond different from the cases in part 1? So all the examples in part 1, I'm just going to use methane as an example. All of them were sp3 hybridized. So say we're reacting that with a halogen radical, X. The halogen radical is going to abstract a hydrogen. So we're forming a bond between H and X. Notice the flow of those electrons. The radical is supplying an electron to abstract the hydrogen. This bond cleaves homolytically. So we form HX plus methyl radical. The carbon now changes hybridization. So we're now sp2 hybridized carbon, and the radical is residing in a p orbital. So why are the examples in problem 4 much higher? So if we consider the ethylene, we're starting off at sp2. When the halogen atom abstracts one of those hydrogen atoms, what this fishhook arrow here is indicating is that that radical is ending up in an sp2 hybrid orbital. Now, why is that? The reason that is because that p orbital is already being occupied by the double bond. Is that clear to everyone? So just so that we're all on the same page, this is your p orbital when you're starting from the sp3 hybrid in this first case here. The single electron that I'm showing there, again, that resides in both lobes of the p orbital. I can't really depict that with a drawing, and it may look like it's only localized in the top thing, but it's not. It's spread out amongst both of those lobes of the p orbital. Are we clear on this? So we're going to move on to question 5 here, which asks us to find the enthalpy change for the following reaction. So we're taking the most basic hydrocarbon, methane. We're treating it with chlorine. We're forming chloromethane plus HCl. So we want to find the enthalpy change. So this is a term you're going to see in chapter 6, enthalpy. So we're really only considering part of the Gibbs free energy equation at this point. So you learned from Gen Chem that the change in enthalpy is the change in enthalpy of the reactants. And notice here, this may change a little bit in how your book presents it. I'm using a plus sign, and I'll explain sort of how this works, plus the change in enthalpy for the products. So generally speaking, the values from the table we're just going to keep those positive because in the reactants we have to break bonds, so we have to put energy into the system. Then for the reactants, we're just going to put a negative sign in front of them because when you form a bond, you release energy as heat. So we're going to leave these positive, we're going to call these negative, and then overall we just add them together. So here's the reaction. Now, if you recall from Gen Chem, you learned about electrochemistry where it was basically half cells overall you had an equation that was an oxidation or reduction, then you looked up those different values. So what we have to do here for this overall reaction, we're going to use the values from the table to look at methane. Notice what's happening, the change between methane and methyl chloride. We're taking methane, homolytically cleaving the bond. So that's sort of one of the half reactions. Chlorine, we're cleaving the Cl-Cl bond. So if we go in the table, let me just ask you, well, we already saw what this value was for the first one. This is plus 435. Now let me ask you, what is the value for chlorine cleaving this bond that I should write here from the table? Just so I know that you're able to look that data up and understand it. Maybe throw a number in the chat. Cole says 243, that's what I got as well. So we're writing plus 243. So we add these numbers together, 435 plus 243, that gets us plus 678. So again, I want you to understand what this number is telling us. For the reactant side of this reaction, we have to put 678 kilojoules of mole per energy into the reaction to get it to move forward to form these products. Now for the products, we're looking at the other half reactions. Notice here, in the forward direction, you're cleaving those bonds. Now to make the products, you're still looking at the same table, but the methyl radical and the chlorine radical combine to give you your product. So what number should I write here? What do you mean by chlorine have two answers again? It has one. It's plus 243. So Hannah says negative 351. Did everyone find that? So Blakely, this number is the sum of these two numbers. So Hannah says negative 351. And then what number should we write here when H radical combines with chlorine radical to give HCl? What number is this? Hannah says negative 431. And then what's the sum of those two numbers together? So negative 782. So now what are we doing? We're taking this number and we're adding that number. 678 plus a negative 782 gives us what number? So negative 104. Again, just so that you understand how I'm teaching you this, I like to keep this center I like to keep this sum, this positive. So because we're putting energy into the reactants, we keep this number positive. Because the products are evolving energy, we keep that negative, then we just add them. So this is negative 104. What is this telling us? When you put in this amount of energy, 687, into this side, this evolves 782. So overall, Hannah says it's exothermic. So again, yes, that is terms that you're going to see in chapter 6. So exothermic deals specifically with enthalpy, delta H. Just so you understand and that I understand you understand, if I was running this reaction in this Red Bull can, which is sugar-free by the way, if I run it in this can and it's exothermic, what does my hand feel? The reaction's exothermic. What does my hand feel as the reaction proceeds? It feels heat. It feels warmer, right? So understand that the reaction is giving off heat. That's what we mean by negative exothermic. If the reaction was endothermic, what does my hand feel? So it feels cold. And to me, that always seems weird, a reaction being endothermic. When it's cold, that means the reaction is taking heat from the surroundings, so the surroundings get cooler. So just off the top of your head, can you think of any reactions you might have learned from Gen Chem that do that? So I guess what I remember is putting some water on the table and then putting a beaker on top of that water and mixing, I can't remember the two chemicals exactly, but when you mixed them, it got cool and it froze the water so that the beaker stuck to the table. So there's really not a whole lot of common examples of that. The exothermic, if you think in the winter, those hand warmers that you put in your pocket when it's really cold out, that's an exothermic reaction. So there's a practical explanation or a practical application of that. So this sheet, which we just did in problem 5 here, that's the basics of calculating enthalpy change. If we're considering the Gibbs free energy equation, you don't use exothermic or endothermic. Do you know what terms you use if we're considering delta G? We're considering the whole Gibbs equation. Exothermic is then, so Hannah says exothermic is exergonic. Mac followed up with the same answer, so endothermic is endergonic. And again, the differences between those two are just what you are considering in terms of the equation. The Gibbs is the ultimate level where you're considering everything. Okay, so now we're moving on to page problem 6. And this is a comparison of all of the halogens. That's step 1 there, X2. We're looking at all the halogen data. Fluorine, chlorine, bromine, and iodine. So step 1, this is called an initiation reaction. The molecular halogen is cleaving to give you 2 halogen radicals. Steps 2 and 3 are propagating steps. So we're talking a little bit about the mechanism now. And again, what are we doing? Wherever there's an X, we're looking at what are the values when we use that specific halogen. So we're populating these different columns, these rows with values from the table using those halogen values. So let me just populate the first row I'm just looking where it says XX bonds in the table. So again, this part of the table where it says XX bonds, I'm just putting those numbers in. So notice we have to cleave. So we have plus 159 for fluorine, plus 243 for chlorine, plus 193 for bromine, and plus 151 for iodine. So let's see if you all follow what this next propagating step is telling us. We're taking an X radical, it's abstracting a hydrogen to make a methyl radical and HX. So what value should I put here? Take a minute. See if you come up with the same value that I got. Remember, this ties back into what we just did. You have to look up this value. You're cleaving this bond. Then you have to look up this value. You're cleaving that bond. Then you're adding those two together. So I'll wait till there's a couple more responses in the chat, just so everyone sees there's a consensus among the answers. Again, in the stop, start, continue feedback, there was some concern about people answering too fast in the chat. There's not much I can do to stop that. People are just going to pop the answer off pretty quick. That should not stop you from responding as well. You should make sure you find an answer, put it in there. If you're not getting what other people get, that's fine. We're here to discuss and understand why that is. So let's kick off this discussion. What number is this? Number is common for all of them, right? But this number changes because the X is variable. So what number goes here? Just for bookkeeping purposes. So Hannah says 435. Again, we're breaking that bond. That requires 435 kilojoules per mole. All we did was find that number from the table. Now for fluorine, what's the value for fluorine that should go here? Negative 569. So as Aiden originally said, this plus that gets you the negative 134. We're gonna sort of run out of time. So what I want to do now, instead of doing chlorine, bromine, and iodine, let's just finish the fluorine so we can talk about what this means. So I want you to do the same thing that you did here. Do it for chlorine, the bromine, and iodine. Put those values in. But now let's consider finishing this column. X2, this value you're just getting from up here. We're dealing now with fluorine, that's plus 159. Now what's changing here, the X, so you have to go to the table and look up what CH3F is. What value goes here? So Mia says 456. So I'm going to throw a negative in front of that. Just because, again, it's on the product side, it's evolving heat. Now, when you add those two together, what number do you get? I'm going to add these two together. What number should I write there? So we get negative 297. So again, we've done this for fluorine. CH3H plus F2 going to CH3F plus HF. So that's what we just did. Again, in general, what we're doing it for all of these halogens to compare these numbers. So I want you to go through, do it for chlorine, bromine, iodine. But now let's consider the case for fluorine specifically. This is called an initiation. We are initiating a chain reaction. This X radical then comes down here into step 2, and it kicks off a propagation. The X radical abstracts a hydrogen. You generate methyl radical plus this. This is a neutral inactive species now. This methyl radical then comes down in a second propagation step. The methyl radical is abstracting a halogen. This is how you get your product. So we've looked specifically where X is equal to fluorine. Notice what we've drawn here. X radical. What happens to that radical? This radical is called the propagating radical, because then it goes back into step 2. So steps 2 and 3 are a chain. So this is a chain reaction. You've probably heard of that, chain reaction. So to answer this question here, the X radical is the propagating radical. Now, what needs to happen in a propagating chain reaction like this? You have to look at these numbers. Step 3 obviously occurs after step 2. Step 3 is what? Exothermic or endothermic? Step 3, it's negative, it's exothermic. This reaction moving this way produces that much energy, negative 297 kilojoules per mole. You can see from step 2 evolves this much energy, right? So it's also evolving heat. They're both evolving heat. So this, when you use fluorine, this chain is like super fast. And you may not see the implications of that just yet. We are running a bit low on time, but what I want you to do is the same analysis for chlorine, bromine, iodine. Then what I want you to do after you put the numbers in there, look at these values for step 3. In the question you're trying to answer, does the heat evolved in step 3 supply enough energy for step 2 to occur? These numbers are going to change drastically, and they're not all going to be negative. So you're looking, does the heat evolved in this step supply enough energy for this step to keep the cycle going. So think about that. Again, use your table, understand your table so that you know where the thermochemistry is coming from. Read Chapter 6 in conjunction with Chapter 7 so you understand. And what we will do on Friday is we will continue on with this analysis. We'll look at those columns. Then we're going to look at getting back to our original question. This CH, remember in propane, secondary was more reactive than primary. We are then going to consider primary, secondary, tertiary with different types of X, either chlorine or bromine, and why it matters when you use a halogen, one's more reactive than the other. So that's where this is ultimately going. We'll look at these reaction coordinates, and you'll see how they differ between chlorine and bromine. And ultimately, Chapter 10 is setting the stage for getting a halogen into a molecule that we can then use in Chapter 7 as a leaving group to do further substitutions and make other functional groups.